All right, hello again. Welcome back to Abstract Algebra 2. Sorry I can't be there for one more lecture, but I'll be back next time. I'm sure I miss all of you. Anyway, today we're going to talk about fields of fractions, and then which is the end of chapter 15 in Gallian, and then we'll continue by starting our discussion on polynomial rings, which will take a few more lectures after that. Anyway, what's the last thing that we did last time? Luckily, I actually have the iPad here, which tells us the last thing that we proved last time was the following corollary, which is if you have a ring that has a unity 1, then if you look at basically 1 added to itself however many times, that gives you a subring that's either isomorphic to the integers if the characteristic is 0, or is isomorphic to Zn if the characteristic is n. Right? So every ring with unity 1 basically contains a copy of the integers or the integers modulo n. Right? And then we said, okay, well, if you're actually a field, well, first of all, that means that you're an integral domain. And we showed that the characteristic of an integral domain is either 0 or a prime. Right? So that means that depending on the case, if you're a field, you either contain the integers or the integers modulo p. Okay? The integers modulo p are already a field. So the first part of this says, if you're a field of characteristic p, then you contain a subfield isomorphic to zp. Cool, clear enough, right? But in the second case, if the field has characteristic 0, then we know that it contains a subring isomorphic to the integers. And what I kind of glossed over was, well, it's a field, it contains something that looks like the integers, therefore it needs to contain something that looks like the inverse of every integer. And then what you get is you get a subfield that's isomorphic to the rational numbers, which are essentially formed by taking the integers and throwing all the inverses of all the elements. It's not quite true though, right? Because you need to throw in more stuff, right? So you can throw in the inverse of all the integers, so you have all the integers, you also have like a half, a third, a fourth, but that doesn't give you 2/3, right? To get 2/3, you need to take 1/3 plus 1/3. Another thing that is sort of weird about this construction is, well, I'll throw in the 1/2, which is the inverse of 2. I'll also throw in 1/4, which is the inverse of 4. But then there's this property that the inverse of 4 plus the inverse of 4 equals the inverse of 2. So I can't just throw in a bunch of elements. I need to understand how these elements are related to one another, right? So today we're going to develop this theory kind of carefully by talking about the field of fractions of an arbitrary integral domain. Okay, so today, throughout R will be an integral domain. So that just means a commutative ring with unity in which there are no zero divisors. Okay, so the prototypical example to have in mind is the ring of integers z, but everything we'll do today will work over any integral domain. Okay, and the idea is, can we construct a field f such that R is a subring of f in the same way as z is a subring of the rationals? Can I actually take an integral domain and put it in a field? And a field where basically every element of the original ring has an inverse? The answer is yes. We can do this by constructing what we call the field of fractions of R, although Gallian calls it the field of quotients. Okay, so my preference is for R mod I to be called a quotient ring. And for the thing that we're about to form, this today, I would like to call that the field of fractions. And I believe this is the more common convention. Gallian likes to call R mod I a factor ring, and he likes to call what we're going to do today the field of quotients. Okay, luckily, in the second row here, we always specify field, so there's not really any danger of confusing the two. But I will more than likely stick to this side if I'm just talking to you in conversation. In the notes, it depends on how closely I want to hew to Gallian. Anyway, here's the big theorem. where we prove that the field of fractions exists, and we, in fact, explicitly construct it. So existence of field of fractions. Okay, so the hypothesis is let R be an integral domain. Okay, then there exists a unique smallest field F. I should say sort of unique up to isomorphism that contains a subring isomorphic to R. This field is called the field of fractions of R. Okay, so I will say that I'll be a bit loose when we talk about the uniqueness. And again, it's unique up to isomorphism. I just want to include this here because, of course, Z is a subring of many fields. It's a subring of the rationals, but it's also a subring of the real numbers. And it's also a subring of the complex numbers, right? And there's even bigger fields, right? So we'll learn about, like, for example, rational functions over the complex numbers. That's where you take a variable x and you allow all rational functions in x. So an integral domain in general will be contained in many fields where it's a subring. But the rationals are unique in a way, right? Because if you want Z to be contained in a field, the field at least needs to contain the inverse of every integer. And if you do that, as long as you've constructed the field appropriately, what you'll get is something that looks like the rational numbers. You can add more stuff, right? The real numbers contain more stuff than you need to have Z be a subring of the field, right? And that's why the prime subfield that we talked about last time ends up being Q rather than any of the bigger fields that Z is contained in. Okay, so I think that Gallian states this theorem a little bit poorly. But therefore, like, I understand why he doesn't want to mess around with the uniqueness, because then you have to talk about field isomorphisms, and it's not really worth it. But we will construct this field of fractions very carefully, and then we'll sort of gloss over that it's in fact the smallest field which contains R as a subring. Okay, so here's the proof. Here's how we construct it. I'm going to define a new set, first of all, S, to be all ordered pairs A comma B of elements of R where B is not 0. Okay, so basically these are going to be like my fractions. I'm thinking of the A's as the numerators and the B's as the denominators. And just like for the rational numbers, we don't allow B as a denominator because 0 is never going to have an inverse, right? Because, yeah, in a field, all non-zero elements have an inverse. So you want to think of these A over B's as fractions. In fact, in a second, we're going to write them as fractions. But we need to pay attention to the fact that when you write a fraction is not the same thing as an ordered pair, right? Because, this is a comment, right? 1/2 equals 2/4. And if I think of these things as ordered pairs, well, the ordered pair 1, 2 is not the same thing as the ordered pair 2, 4. So what I want to do is I want to define an equivalence relation on S such that 1, 2 and 2, 4 become equivalent under this equivalence relation. Okay, so what's the equivalence relation going to be? We define an equivalence relation, which I'll denote like this on S by, I'll say that two ordered pairs are equal if what? Well, what does it mean to say that two fractions are equal, right? When does A over B equal C over D? Well, we learned a long time ago that you can cross multiply. So this happens if and only if AD and BC are the same integer. And so that'll also be our equivalence relation on S. Okay, and again, we're taking ring elements from the ring R. So AD and BC both make sense, and we can tell whether or not they're equal in R. Okay, so now we're going to let F be a set of equivalence classes of S. And for the ordered pair, the equivalence class of X comma Y, we write X over Y, or X slash Y, right? So we're trying to mimic the construction that we have for rational numbers. Really, a fraction is not just a numerator and a denominator, but an equivalence class of numerators and denominators, right? So this F is going to be our field of fractions. Right now, we've defined it as a set. It's a set of all equivalence classes of ordered pairs. Now, how should we define addition and multiplication? Well, we're gonna take a note from how we do it for the rational numbers, right? So if I take one equivalence class, A over B, and I add it to another equivalence class, C over D, every Russian schoolboy could tell you that this is AD plus BC over BD, just by getting a common denominator. Okay, now what we need to show eventually is we need to show that this definition is well defined, right? Because there's more than one way to write the equivalence class. I mean, there's more than one member of the equivalence class A comma B. There's more than one member of the equivalence class C comma D. If you choose different members, will you get the same result? The answer is yes, but we need to show that. And then we're also going to define multiplication of A over B times C over D to be AC over BD. Okay, so in a field of fractions, it behaves really just like the rational numbers. We just need to make sure that these things are well-defined operations. Okay, but actually the first issue of well-definedness, before we do anything else, is to make sure that this claimed sum, AD plus BC over BD, is actually one of the equivalence classes. Why do I say that? Well, if BD were 0, this actually wouldn't be one of the equivalence classes in F, and so it'd be not well-defined for the reason of the sum doesn't land in the correct place. But of course, since R is a domain, and we know that B is non-zero and D is non-zero, therefore BD is non-zero because in an integral domain, there are no non-zero divisors. There are no zero divisors, right? Same thing here, right? So these are, in fact, at least legal possible sums and products. Okay, so we need to check well-definedness now because there are many representations of the same fractions in F. Then, once we show that the operations are well-defined, we then need to show that those two operations make F into a field. Okay, so let's suppose that we have two representations of A over B and two representations of C over D. Right. I need to show that if I add A over B to C over D, and I add A prime over B prime to C prime over D prime, that the sum that I get is actually the same thing, right? Same thing with the product. So which order do I do it in? I do it in the sum order first, right? So A over B plus C over D is of course just defined to be AD plus BC over BD, whereas A prime over B prime plus C prime over D prime is defined to be A prime D prime plus B prime C prime over B prime D prime. So the question is this fraction the same as this fraction? Well, what's the equivalence relation? The equivalence relation is equivalent to cross multiplication, right? So we want this fraction to equal this fraction. And the equivalence relation that we've placed on these ordered pairs is this happens if and only if AD plus BC times B prime D prime is equal to A prime D prime plus B prime C prime BD. Of course, I mean, we want that shows that this equality holds in R, right? But this is just a matter of multiplying out, right? So AD plus BC times B prime D prime is AD B prime D prime plus bc b prime d prime. Okay, well, now let me use the fact that a over b equals a prime over b prime. This is the same thing as saying that ab prime equals a prime b. So if I see an ab prime, I can replace that with an a prime b. Similarly, cd prime equals c prime d. So if I see a cd prime, I can replace that with a c prime d. So this is a prime. I'm going to rearrange factors a little bit to make it clear. A prime d prime bd. So I've just replaced the ab with an a prime, the ab prime with an a prime b, and then the other one I'll get, again, I'm going to rearrange a little bit here. Let me not do it yet. B c prime b prime d. Okay, but now it's easy enough to see that this is exactly this, right? Those are both. We can push the b prime, the bd to the right side. B prime c prime bd. Okay, that's a relief. Addition is well defined. That means that the addition that you've been doing on fractions your whole life actually makes sense. It doesn't depend on your choice of numerator and denominator for that fraction, right? Okay, we should show that multiplication is well defined. So also we want to show that AC over BD, we want that this is equal to A prime C prime over B prime D prime. But this happens if and only if AC B prime D prime is equal to A prime C prime BD. But now we just make use of this twice, right? We already said that AB prime is the same thing as A prime B. And we already said that C D prime is the same thing as C prime D. And so those are in fact equal because A over B equals A prime over B prime and C over D equals C prime over D prime. Okay, so hence the addition and multiplication are both well defined. Okay, now I need to show that F is actually a ring. So I need to show that it's an additive group first of all. Okay, so first of all, for the plus structure, 0 over 1 is the additive identity. Why is that? Because 0 over 1 plus any A over B, by a rule you get a common denominator, but here the common denominator is B. You would get 0b plus 1a over 1b, but that's just a over b. And similarly on the right. So 0 over 1 is the additive identity, as you should have been able to guess, right? The additive inverse of a over b rather, is just negative a over b. You can show that. It's probably a good exercise. I mean, it's not a good exercise because it's just addition of fractions, but it can be shown that this is just the same thing as negative a over b. You can show that this is a commutative associative operation. So maybe I'll say check that plus is commutative and associative. For the ring structure, 1 over 1 is the multiplicative identity. That one's easy enough to see from the definition of multiplication. And here, if A over B is a non-zero element, what does that mean? That means that A over B is not equal to 0 over 1. Because that's the zero element of F from when we looked at the additive structure. And that's the same thing as saying that A is not equal to 0. So the non-zero elements are just exactly the ones whose numerators are non-zero. That shouldn't be a surprise. But that means that if I take a non-zero element, I can define its inverse to be B over A. This fraction makes sense because if A over B is non-zero, it means that A is non-zero, therefore it's an allowable denominator. Right? And so it's quite easy to see that if you multiply A over B times B over A, you get AB over AB, which is equal to 1 over 1, in the equivalence relation, right? Because if you cross multiply, you get AB equals AB. Okay, and then just check distributivity, really. I guess you have to check associativity and multiplication, but that's easy. Multiplication is a much easier operation on fractions than addition, right? Okay, so what we've done is we've constructed a field, F, by essentially taking fractions of elements of R with non-zero denominator. We still need to make some argument as to why R is a subring of F, and in fact F is the unique smallest field which is isomorphic to R. So how do you show that it's a subring? Well, there's a mapping. The mapping phi from R to F, where you just send the element R to the fraction R over 1. I have a small error in the notes, but let me fix it. You can show that this is a ring homomorphism, injective ring homomorphism. Okay, so you should check this. The elements R over 1 behave just as you'd expect. If you add R over 1 to S over 1, you just get R plus S over 1. R over 1 times S over 1 is clearly RS over 1. And again, the only fractions that are equal to 0 are the ones whose numerators are 0, which shows that this is an injection. So I should say an injective ring homomorphism. In other words, R is isomorphic to phi of R, which is a subring of F. Therefore, F does indeed contain a subring that's isomorphic to F. Okay, and then let me just gloss over this. Any field that contains R as a subring at least needs to contain every inverse of elements of R, and therefore also needs to contain all sums of the inverses of the elements of R. And it can be shown, I'm not going to show it, I'm not going to assign it as an exercise, that basically that means that the inverses of R have to add just like fractions do, right? 1 over A, once you have 1 over A and 1 over B, you're sort of forced into this relation like this. Okay, so I'm going to hand wave this. Gallian doesn't bother to mention it at all. I basically just want it in the statement of the theorem to make the statement of the theorem correct. Okay, so okay, so that's the field of fractions, and it's a very intuitive construction because we worked with fractions most of our lives. For you, I don't know, when did you learn fractions? 15 years ago. For me, it's more like 30 years ago, right? Anyways, let's look at some examples. So of course, just for today, I'm going to use the notation frac of R to mean the field of fractions of R. It's not standard, so really we should just say the field of fractions of R as Gallian does. But for now, to make these notes a little bit simpler, let me just say that. So, of course, the field of fractions of Z is just isomorphic to Q. That's the construction that we were basing it on, right? Q can be viewed as equivalence classes of pairs of integers with the denominators non-zero with the addition and multiplication operation that we defined in the field of fractions. Okay, a homework exercise is if F is a field, then the field of fractions of F is just F. Okay, this of course follows immediately if you take my word that F, the field of fractions, is the smallest field which contains the ring. But you can show directly that if you take this set of equivalence classes, you actually just get something that's isomorphic to F again. So it's in the tentative problem set exercises. I may assign it, I may not. Okay, here's something that I alluded to a second ago. If F is a field, I can consider the ring R to be polynomials in one variable over F. And what the field of fractions, right? So R is an integral domain, but it's not a field anymore because X does not have an inverse. But the field of fractions ends up looking like, all quotients of polynomials, f of x over g of x, where g of x is non-zero. So it's all polynomials over polynomials where the denominator is a non-zero polynomial. From calculus, that's just called a rational function. So this is called the field of rational functions. Over f, or with coefficients in f. And we denote it f parentheses x rather than square brackets. Okay, so square bracket, that's polynomial ring. Curvy brackets, parentheses, that's like a field extension. That's the field of rational functions in one variable over x. In this field, every non-zero polynomial does in fact have an inverse. The inverse of f of x is just 1 over f of x, right? So this, for example, allows us to create very big fields. So here's our first. If we let the field be ZP now, this is the field of rational functions with coefficients in ZP. This is our first example of an infinite field that has characteristic P, right? The elements here are just rational functions, a polynomial in ZP over a polynomial in ZP, a non-zero polynomial in ZP. But it's still true, right? Because the coefficients are here coming from ZP, that if you add an element to itself P times, you'll get 0, right? So this is an infinite field of characteristic P. Okay, and then if we take Z adjoin X as our ring, then the field of fractions of Z adjoin X, well, it's just all rational functions now where the numerator and the denominator are integer polynomials. Right, so you're just, this is like a subfield of like R or Q, in fact, the field of rational functions with coefficients in Q. But notice that we've inverted every constant polynomial, which means we have inverted every integer. And so the prime subfield here is Q. We do get a copy of Q, which we're guaranteed to in any field. Either get a copy of Q or a copy of ZP. Right, so here Q is the prime subfield, where you take Z, the constant polynomials and their inverses. Okay, so that's the field of fractions. If you're a graduate student in this class, I'm going to send you an extra thing to read on general localizations. Let me just say a word about that to all of you, just so you know. So here what we did is we took an integral domain, we took all non-zero elements, and we gave them inverses, and we constructed this new field, right? Now there's no reason that you have to take all of the elements in the integers and invert them. You can sometimes take a smaller set of elements in your integral domain and just try to add just those inverses. Okay, you can't do this for any set, but it's possible to pick nice sets for which you can do this, and you can create bigger rings that contain more inverses without going all the way to being a field. And this is the general theory of localizations, but if you need to understand localizations, like if someday you want to take algebraic geometry, you can learn it then. For now, just try to understand the field of fractions. If you're a graduate student, then I'll make you learn it now. Okay, so our next topic is the topic of polynomial rings. Okay, this is chapter 16 in Gallian. I guess that's what it says up there. So we've already seen many examples of polynomial rings in this class. right? But we haven't rigorously defined them, and we haven't studied them tons yet. So today, what we'll do is we'll give a formal definition in almost full generality. And then we'll spend the next couple of lectures studying polynomial rings. We'll spend even a couple more lectures studying divisibility in polynomial rings. These are super duper fundamental examples in ring theory. Okay. In fact, they're the basic objects of study. They're like the most basic objects in algebraic geometry, which is one of the hottest fields in mathematics at the moment. It's incredibly deep, incredibly powerful. We don't actually have any algebraic geometers on faculty. I might be the closest thing there is to an algebraic geometer. But let's say you go to graduate school in mathematics, you may decide to do what all the cool kids are doing and study algebraic geometry, maybe. Okay, so let's define a polynomial ring. So far, we've sort of been relying on our intuition for polynomials, but here's the definition of a ring of polynomials. Okay, so let R be a commutative ring. Okay, and this assumption is why I'm saying we're defining them in almost full generality, because you can allow non-commutative base rings, but then you should actually define something a bit more general than what we're going to define here. So we're just sticking to the commutative case. We're about to define commutative polynomial rings. Okay, now we're going to define the set of formal symbols R adjoint X is the set of all formal symbols of the following form: A naught plus A1X plus dot 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 plus AN X to the N, where N is some non-negative integer, and each of the AIs live in R. Okay, now what do I mean by formal symbol? Okay, so what does a mathematician mean when they say formal symbol? What we mean is that literally we're just defining these symbols as the elements of our ring. Okay, so for example, like one of the formal symbols that we've just defined is the symbol 1 plus x. Right? That's A naught is 1, A1 is 1, as long as R is a unital ring, but one of the symbols that we just defined is 1 plus x, right? What we're saying when we say that it's a formal symbol is that we're not assuming anything at the beginning about how the different symbols are related to one another. Right? So for example, 1 plus x looks a lot like it means 1 added to x. But if it's just a formal symbol, I'm not assuming that at the beginning. I'm not assuming that the symbol 1 plus x is related to the symbol 1, which is also in this ring, this set, or the symbol x. Okay, so what we're doing is we're just saying, okay, well, what a polynomial is to start with is it's just an expression of this form, and we're going to be totally agnostic about any of its properties, and then we're going to declare its properties later. So in the end, it will be true that 1 plus x as a polynomial is in fact the sum of the polynomial 1 and the polynomial x, but that's why the notation is good, but we're not, like, it's not true because of the notation. The notation will just reflect the fact that it is true because we'll define it that way. Okay, similarly, another symbol that we've defined here is the symbol, 1x squared. Now, it's just a symbol, right? It's just a symbol x squared. It looks like it might be x times x, but at this time, I have not yet defined any multiplication here, so x times x doesn't make any sense yet. Eventually, x squared will in fact be equal to x times x, but at the moment that we're defining the set, we're just defining x squared as a formal symbol. Okay, hopefully that makes sense. This set with an operation we'll define soon, with operations to be defined soon, is called the ring of polynomials over R in the indeterminate x. Okay, oftentimes we'll use the word variable here also, in the variable x. Okay, so as a set, it's just a set of all formal symbols. It will eventually have an addition and a multiplication that will make it a ring. Okay, we should say when are two of these formal symbols equal? So two elements, what do two elements look like? One element looks like a naught plus a1x plus dot 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 plus a and x to the n. And another element looks like b naught plus b1x plus dot 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 plus bm x to the m. Might be a different m, might be a different m. These are equal if, first of all, n is equal to m and ai equals bi for all of the i's. Okay, and one thing that we'll do here is, okay, I'm saying for all I. Now, I haven't told you what I ranges over, but when we talk about formal symbols in this polynomial ring, we can just define any ai bigger than n just to be equal to 0. So we'll do that often, right? So we often will assume, or we'll declare that if I is bigger than n, ai is just equal to 0. Same thing for the bi's, right? Okay, so before I define an addition and a multiplication, which, by the way, are the ones that you expect. This is not like some exotic object. We're just trying to be very careful when we define it. Once we've defined it carefully, then we can, we can work with it as we're used to. Beyond my remark about what does a formal symbol mean, let me also note that we're using, there's a couple things here. First of all, like x in like algebra when you're in middle school sometimes means, oh, an unknown but fixed element in the real number, say, right? So if you say like, oh, 3x plus 7 equals 10, what the x represents there is you're solving for x. You're trying to find the real number x that makes it true when substituted in, right? So in this polynomial ring, the symbol x is really just a symbol. It does not represent some unknown element of R. That's why it's sort of preferable to say indeterminate. It's just not it's just a symbol, right? So essentially all we're doing in this polynomial ring is we're using the symbol x, x squared, x cubed, etc. as just placeholders just to separate ring elements, right? You could also define polynomials as just a set of all finite sequences of elements from R, right? So like a naught, comma, a1, comma, a2, dot, 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 comma, an. You could think of that, right? The powers of x are just serving as placeholders to separate the different elements of R. The reason why this is preferable to using finite sequences is that, of course, we're perfectly used to adding elements like that look like this. Okay, so a subtler issue that actually does matter is, in general, we should not confuse a polynomial in Rx, adjoint x, which is just a ring element, with the function defined by that polynomial. Right? So in calculus, generally when you talk about a polynomial, you're thinking of the polynomial very often as a function from R to R. Right? So it is true. It is true in calculus. If you write down the symbol x cubed, you often think of it as a function from R to R that takes the element a and substitutes it into the polynomial. Right? It's just the thing that cubes the polynomial. Now, it is true that we can think of polynomials as giving functions from the base ring to the base ring. That actually is true where you just substitute in, right? So it is true that we may regard a polynomial f of x in R adjoint x as a function. from the base ring R to the base ring R, where you send the element A, you just plug it in for X in the polynomial. Everywhere you see an X, you plug in an A, and then you do the operations in the ring, right? So frequently that is actually genuinely useful, right? And we'll use it all the time, right? However, the polynomial is not the same thing as the function, because sometimes different polynomials give you the same function. So a polynomial is not the same thing as a function. Although given a polynomial, it is oftentimes useful to think about the function that it gives, right? So the easiest example here is if we consider the polynomial x cubed in Z3 adjoint x. Well, what does x cubed do as a function? Well, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8, which is 2. So as a function, x and x cubed give the same function, I guess I should say. But x, the polynomial x, is not equal to the polynomial x cubed. So the functions are the same, the polynomials are different. It is useful to think of polynomials as functions on the base ring. We will do it often, but you don't want to get confused and confuse the polynomial for the function, okay? Let's now define addition and multiplication. Okay, and really it's just what you would expect, right? So for this part of the lecture, you can just I don't know, check Facebook or whatever you do. It will be what you expect. Let R be a commutative ring. Do kids still use Facebook? Comment below. Okay. If I take two elements, f of x, g of x, and then polynomial ring over R, I can write them, you know, a naught plus a1x plus dot 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 plus a n x to the n, and b naught plus b1x plus dot 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 plus bmx to the m. And in the ring, we define the sum to just be the polynomial that adds together the a0 and b0 terms, the a1 and b1 terms. You just add the corresponding coefficients in R. And then you go until whichever one is bigger, right? So I don't know whether m or n is bigger in general, but where s is the max of m and n. And again, we do this is why it's convenient to say that, okay, everything that's larger than the nth power is just declared to be 0 in f of x. Everything that's larger than the mth power is declared to be 0 in g of x. And so therefore, even though, you know, let's say that n is bigger, technically bn is not defined in g of x, we've declared it to be 0, and so this formula makes sense. Okay. Further, we also define f of x, g of x. This is the one that's slightly trickier, right? So how do we do it? Well, how do you get the constant term of f of x, g of x? You just take the constant term of f times the constant term of g. Okay. How do you get the degree 1 term? Well, you have to take a naught plus b1 plus a1 b naught, right? There's two ways to get a degree 1 term. You can take those two and multiply them together. You can take those two and multiply them together, and we should add them up. How do you get the x squared term? Well, you take a naught times b2x squared plus a1x times b1x plus a2x squared times b naught. Right? So how should I write this down? Well, the definition, it will be c naught plus c1x plus c2x squared plus dot 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 plus, it goes up to degree m plus n, where we define ck to be the product of all of the coefficients where the indices on a and b add up to k. Okay, this is the normal definition of multiplication in a polynomial ring, where basically you do it term by term, and then you collect like terms, and then that's the coefficient that you get on the powers of x. Okay, so yeah, it's just the usual notion, right? So there, if you look at example 82 in the notes, we've done it in Z5 adjoin x. Make sure you read through that. Trying to keep these lectures a bit shorter than normal, so let's not belabor adding and multiplying polynomials. I've already belabored it a bit too much. Okay, let me just note here that we haven't checked that it distributes, that multiplication distributes over addition. We haven't checked a lot of things actually, but first of all, it's easy to see that addition of polynomials and multiplication of polynomials is commutative, because we're assuming that R is a commutative ring, and therefore the addition of the coefficients is commutative, and the multiplication of the coefficients and the addition thereof is also commutative. I guess we don't need it for addition. For addition, it works because the addition in R is commutative. But okay, associativity of addition, that's easy, but multiplication, and it's a weird multiplication operation when you write it down like this, right? And so checking associativity and distributivity is a little bit annoying. Therefore, you can do it if you want to, but I'm not going to ask you to do it. Okay, basically, trust me, trust yourself, that this does in fact make the polynomial ring into a commutative ring, right? Because we said multiplication ends up being commutative. Okay. So trust that R join X is a commutative ring. Okay, if you're untrusting, or if you are eventually going to be an algebraist, you should just check for yourself. It's easy to check, it's just tedious. Okay, I'm going to make some definitions that should be very familiar. In the polynomial ring R join X, here I'm assuming that R is a commutative ring. Let's take the polynomial f, and okay, one thing that I'm going to do in this class, which you will also do the rest of your life, is oftentimes switch in between whether I'm writing the powers in decreasing order or increasing order. There's reasons to do both depending on what you're doing. So here, I'll write it in decreasing order. Right? You should write it in one or the other in general, but which one you should do depends on the context. And let's assume that we've written it in a non-stupid way, right? In other words, an is non-zero. If an were 0, we could just drop all the 0 terms until we get to the top non-zero term, right? In this case, we say that f of x has degree n. Its top non-zero coefficient happens in the x to the n term. We call an the leading coefficient of f. Okay, we'll often write degree f of x is equal to n. Okay, now what happens if there is no non-zero coefficient? In other words, what happens if the polynomial is f of x equals 0? Okay, in this case, we're just going to take the convention that f of x has no degree. Okay, there's a couple of competing conventions here for this. Now, I would say that if it's me, it seems like all the constant polynomials should have degree 0. Right, so why do you want to say that has no degree? Okay, so the reason is just that it's useful. More nice statements are true when you make this convention than if you make some other convention. For example, it's kind of very useful to say that, actually, let me make one definition first. Polynomials of the form just a single term, x to the n, are called homogeneous. Homogeneous of degree n. Okay, now that I've had this definition, it's kind of useful for me to say that, oh, if you add two homogeneous polynomials of degree n, you get a polynomial of degree n. Right? It's true it's true unless you say that, unless you notice that, well, if you take a n x to the n minus a n x to the n, those are two homogeneous polynomials of degree n, and you actually get 0, right? Now, this isn't fixed by saying that 0 has no degree, but what I'm trying to say is that basically you want to view 0 as if it kind of lives in every single degree, right? So because oftentimes you want to view 0 as living in every single degree for certain statements, therefore it doesn't really have degree 0, it really has no degree. Okay, another reason that's useful is that if you take a degree m polynomial and you multiply it by degree n polynomial, then what do you get? If you said a degree m plus n polynomial, then you're morally correct, but you're technically wrong. Okay, so first of all, if if the leading terms happen to multiply out to give you 0, you'd get a polynomial of smaller degree, right? So for example, if we're working in the coefficient ring z6, and you take 2x times 3x squared, you get 6x cubed, which is 0. You could fix that, of course, by saying, okay, well, suppose that R is an integral domain. But in that case, if you take the 0 polynomial times any polynomial, you won't add the degrees together, right? If you said that the 0 polynomial had degree 0. Okay, so for that reason, some people say that 0 has degree negative infinity. And then it makes that statement true that if you take a polynomial of degree m and a polynomial of degree n, and you're in an integral domain, then you get a polynomial of degree m plus n. So you could take that that convention, but it will be more useful to us to just say that the 0 polynomial just doesn't have a degree. The degree of the 0 polynomial is sort of not defined. Okay, these are my technical tangents that don't matter that much, but I care very deeply about, right? Let's continue. If the leading coefficient of f of x is the unity of R, of course here I'm assuming that R has a unity in this case, then we call f of x a monic polynomial. So a monic polynomial is one whose leading coefficient, the largest degree term, has a coefficient of 1. And yeah, homogeneous polynomials of degree 0 union the 0 polynomial are called constant polynomials. Okay, like I will often also probably say things like linear polynomials, quadratic polynomials. They are just the things that you expect. Okay, so I guess that's enough for today. Today we defined fields of fractions and we defined polynomial rings. Now I belabored lots and lots of points, but the idea should be that these things are actually very familiar objects. The field of fractions is new, but it kind of mimics how the rationals work. Polynomial rings are also new, right, in that they can have arbitrary base rings, so they can have different properties, but we're used to polynomial rings, at least over the real numbers from calculus. Yeah, let's have some short-ish lectures this week, just because I'm gone. I didn't have enough time to, I didn't take time to let you ask questions and stuff. We'll jump into the proper study of polynomial rings when I get back next week. All right, good work, everybody. See you next week.